Hello everyone. I hope you people are doing fine. So my name is Ajay Gagat and I'll be your physics mentor for the session. So I'll be giving you a little demonstration on a very important topic of the mechanics. So the mechanics part. So I'm going to start with the very basic definition of work. So when we are going to start with the definition of work, we generally start it like this. So let me change the color of my pen. So we write work done as F dot ds. So we generally start with the definition of work done as F dot ds. When I write F dot ds, I can safely write it as F as mass into acceleration dot ds. If the angle between them is zero, I can safely write as it to be ds only. And since I can always write acceleration as dv by dt, okay, let me just change the thickness of my pen to a little more. So I can write this as m into dv by dt times ds. Hopefully, you all know that I can write this expression as mass into dv and I can write it as ds by dt. So ds by dt is actually the velocity. So I can safely write this expression as m into v into d. So this is my expression, which looks like this. So this F, when I wrote F is equal to ma, it means this F is the total force. This F is the total force acting on a object. So when I write F as m into a, where a is the acceleration produced in the body, so it means I'm writing this F as a total force acting on the body. So to find out the total work done, I can safely integrate the expression if I put the integration. If the initial velocity is u and final velocity being v, I can safely write down. So this is the small work done. Integration will give us the total value of the work done. So the total work done will comes out to be m v square by 2 minus m u square by 2. If you can recall this term as mv square, this expression is called as kinetic energy. And since v is our final velocity and u is our initial velocity, I can safely write this as kinetic energy final minus kinetic energy initial. Since this F is a total force, so I can safely write work done by all forces. Work done by all forces acting on an object. Work done by all forces acting on an object. All forces acting on an object. Acting on an object. On an object is equal to is equal to is equal to, you see kinetic energy final minus kinetic energy initial, I can safely write it as change in kinetic energy. I can write it as change, I can represent with delta kinetic energy. And my dear student, this is one of the very important expression which we are going to use often to solve our problems nicely. So this statement, work done by all forces on an object is equal to change in kinetic energy, is called as work energy theorem. This is called as work energy theorem. So it states that when a system of forces are acting on an object, when a system of forces is acting on an object, maybe friction is there, normal is there, mg is there, some external agent is also there. So work done by all those forces is simply as if we calculate the change in kinetic energy. That is final kinetic energy minus initial kinetic energy. So this is termed as work energy theorem. Now we are going to demonstrate one problem on that. So it is always uh, always helpful to do some problems. So we have this problem. So let me change the color of my pen. So let me make this time as black. So the problem is quite easy. We have a block of mass we have a block of mass 10 kgs, 10 kg, and the coefficient of friction being 0.4. 0.4 is the coefficient of friction. It is placed on a surface initially at rest. Now a force of 50 Newton is applied on the block. Now a force of 50 Newton is applied on the block. And the question is asked is, find work done by all the forces acting. Find work done by all forces. Find work done by all forces. All forces acting on the body. Acting on the object. Or I can write on the body. Acting on the block. So you see, if we refer to the free body diagram, so then definitely there is one force as normal force, which is acting upwards, and mg is acting downwards. So find work done by all forces acting on the object in the first 2 seconds. In the first 2 seconds of motion. In the first 2 seconds of motion. Seconds of motion. So I think the question is quite clear. We have a body of mass 10 kg. It is placed on surface where the coefficient of friction is 0.4. Now a 50 Newton force is applied on the mass on the 10 kg block. So we have to find out work done by all forces acting on the block in the first 2 seconds. So we remember that work done is simply F dot displacement. We can find out the displacement in the first 2 seconds. So we can find out the displacement in the first 2 seconds. And this is how we are going to calculate the work done by each force. So we are going to calculate the work done by each forces. You see, in the horizontal direction, the net forces F net in the horizontal direction is going to be, to find the acceleration, F net in the horizontal direction is going to be simply 50 minus mu mg, that is 0.4 into 10 into g. So that makes it 10 newtons. I hope this F net can be written as mass into acceleration. So the acceleration in the positive x direction comes out to be 1 meter per second square. So acceleration in the horizontal direction is 1 meter per second square. Initially, the body was at rest. I can calculate its displacement in the 2 seconds. I can safely write S is equal to ut plus half at square. That gives me u being initial velocity as 0, half a is 1, t is 2 seconds. That makes it 4. So the displacement in 2 seconds is coming out to be 2 meters. We can also calculate its velocity in the 2 seconds. I can write v is equal to u plus at, u being the initial velocity. So after 2 seconds, the velocity of the body is going to be simply 1 into 2. That is 2 meters per second. So now we can simply calculate the work done. We can simply calculate the work done by our usual method first. And then, since work done is a scalar quantity, to calculate the total work done by all forces, we will simply add them. So work done. So let me use this color. So work done by gravity. So work done by gravity. Since mg is acting downwards, and the displacement is in positive x direction, so angle between them is 90 degree. I can safely write 10 into g into displacement is 2 meter into cos 90. So it is going to be 0. Similarly, I can write work done by normal reaction. Normal reaction is also perpendicular. So it is going to be 10 into 10 into 2 into cos 90. So this is also going to give me 0. Now we are left with 2 forces. That is work done by external agent. So let me calculate work done by 50 newtons. So 50 newtons is in the positive x direction and the displacement of the body is 2 meters and the angle between them is cos 0. So it is going to be 100 joules. Now, friction. So work done by friction. So friction is acting in the opposite direction. Okay, let me just select the pen. So work done by friction is going to be mu mg cos theta into mu mg cos into mu mg, that is mu is 0.4, m is 10, g is 10 into angle between displacement and friction force is 180 degree, that is cos 180, which is -1. I can safely write, let me just make a little space. I can safely write this as this is going to be mu mg cos into displacement. Displacement is how much? 2 meters. So this is going to be, if we calculate it, so it is going to be -80 joules. So total work done by all forces is coming out to be simply the scalar addition of work done by individual force. I think total work done comes out to be simply addition. So total work done is going to be simply addition. 0 plus 0 plus 100 minus 80. So that comes out to be 20 joules. So this is how, if we want to solve this problem using the definition of work. So this is how we are going to do that, since we remember the basic definition. But shortcut trick could be if we directly use work energy theorem. What if I will apply work energy theorem? So work energy theorem just states that work done by all forces is equal to change in kinetic energy. So I can write work done by all forces, total work done, is equal to change in kinetic energy, that is final kinetic energy minus initial kinetic energy. So initial velocity is 0. So initial kinetic energy is going to be 0. Finally, it is going to be half into 10. Velocity is how much? 2 meters per second. That is going to be 4. So you see, it is 2. So this is simply 20 joules. So this is how we have done it in just 2 steps. If we could have the knowledge of work energy theorem earlier, we could, instead of solving work done by each force and then summing up to get total work done, we could have solved it in just one step using the work energy theorem. So work energy theorem in most of the problems is very helpful. So this is all about the work energy theorem. I'll again tell you the statement. It states that work done by all forces acting on an object is equal to change in kinetic energy. So similarly, we can solve more problems. Thank you so much for your patience. Have a nice day, everyone.